Okay, I'm going to go over part 7.3 on this. I'm going to show you the mark scheme for these first two rather than write it down. But basically, what you've got here is grey code, encoded disk. Obviously, the pendulum will swing as the car goes up and down ramps and things like that off-road. Obviously, it's going to give you an answer, a binary, an answer in grey code. Now, obviously, what's the difference between grey code and binary code? The main difference is grey code only gives you one change for every segment. Binary code can give you several changes. What do I mean by that? Well, if you went from binary, you've gone. Let's go from 0, 0, 1. Next one in binary will be 0, 1, 0. You've got two changes there. Look, the least significant bit and the one next to it changes. Grey code, you only get one change for every binary level. Okay, so what's a disadvantage then of using binary code rather than grey code? We can get errors, can't you? If it's just teetering between this change here, then it might be that this 1 goes to a 0 first. So it might be you might get 0, 0, 1, and then just for a very brief amount of time, might go 0, 0, 0 before getting 0, 1, 0. So that kind of mid bit, that'll give you a false reading. The grey code, because you've only got one change per segment, will not give you that. Okay, now the mark scheme says similar to that. Feel free to read it yourself. The grey code only one bit changes, and they've given you an example there using the opto switches. Okay, so have a little read of that one. Okay, on to the next question. This is to work out now the resolution. The resolution is the smallest voltage step. Okay, so there is an equation on the data sheet for resolution as well. So you can look on the data sheet for your equation. So the resolution equals, in this particular case, there's voltage change, but obviously it's not voltage change. In this case, it's angle change divided by 2 to the power n, where n is the number of bits. That's my angle, by the way. I can't really draw it very well. There we go. It's my angle change there. Okay, over that. So in this particular case, what is the angle? Now, this is where it's a bit annoying because obviously it doesn't tell you what the angle is. So if you get obviously your protractor out, you can measure that angle. It's about 120 degrees. Now, in the exam, they wouldn't expect you to have a protractor, so they would have to tell you that in the exam. They would say the angle it's measuring is this. So in this particular case, quite simple. Resolution is 120 over 2 to the n. What is n in this case? It's 3-bit, isn't it? Yeah. So 2 to the power 3 gives me 15, I think. 15 degrees, yeah. Hope that makes sense, 15 degrees. Now, what would be the minimum number of bits if I wanted to change the resolution to at least 10 degrees? I think they made a mistake on it. I think that should say most 10 degrees, not least. But I'll show you why in a minute. So what would I need to do that now? So now you're kind of working the equation backwards. So I need 10 degrees and I want to find the resolution. Okay, and I need to find a number of bits. Okay, so how would I actually work that one out? So theta divided by 2 to the n obviously is going to give me where are we? Is going to give me 10 for resolution. Okay. So basically 2 to the n. It's 120. That's why, yeah, 120 is that. Yeah, that's the resolution. So I do apologize. Yep. So we're rearranging now to work out 2 to the n. Sorry. So 2 to the n equals that over that, which gives me, in this particular case, 120, which is 12. Okay, so that's the answer. 2 to the n is 12. So we need to think of how many bits would that be. Well, if 2 to the 3 is equals 8, 2 to the 4 equals 16. So do you think 3 bits or 4 bits would be all right? 3-bit would not work, so it's going to be n equals 4. N equals 4 bits. because it needs to go over that number, n equals 4 bits, okay? That is the answer. That's why it's a bit of a weird one, because if you work this backwards now, so therefore, working the equation backwards, the usual equation, there's my resolution. If I work that backwards, here's the equation again. So this time I'm going to stick in 120 degrees over 2 to the 4. We'd actually get 7.5 degrees. So just make that in a different colour, just so you can see. There we go. So just make that a different colour. So actually, I think it should say maximum of 10 degrees, not minimum of 10 degrees. Okay. So I think they've kind of made, as they usually do, make a mistake in this. Right, this is straightforward. Remember how we do this now? We look for things. So we got to basically look at Boolean algebra for this. So this bit, we look over here and see, is there anything unique? Does it look like either Z, Y, or X? Straight away, I know it looks like Y. That's dead easy. Looking at the next one. Does this look like Z, Y, or X? No. Then you need to tie in two things. Does it look like two of these? Well, look, we've got Z and no, that doesn't. That only that happens above, so it can't be that. What about not Y and X? When does that next happen? Oh, look, that actually only happens there and there. So straight away, I know it's not Y and X. Now, if you struggle with that idea of just being able to spot it like I can, don't worry about it. Look what you can do. Use the old classic Carnot map. Yeah, just use a classic Carnot map. Z, Y, X. Put your ones and your zeros in. Get your groupings, and you will get an answer. Yeah, I should say Z, Y, X. So I do apologise if I've done that a bit quickly. There you go, too quickly. Put your ones and your zeros in. R. Have a go at doing both. Feel free to pause it now. See if you can find R using the Carnot map, or trying the other way of just being able to spot it. Okay, hopefully you got the right answer. It is not Y and not X. Not Y and not X. Okay. There we go. Okay, there isn't what I'd probably recommend doing before you listen to me on this one is read up on this above. Okay, it's got block diagram. It shows you what a rotational speed is and what an incremental encoder is. It basically just gives you some ones and zeros. Have a read before. So pause me, have a little read of it just above, and then have a little look at this. Okay. Okay, right. So I've got 40 transparent slots and I've got 800 pulses. So first of all, we can find the amount of resolutions. 800 over 40 gives me 20 revolutions. Okay. Now I've gone 20 revolutions. It says it does that in 10 seconds. So let's find out how many resolutions it does in 1 second. So in 1 second, we get 20 over 10 equals 2 revolutions. So 1 second, we get 2 revolutions. Okay, it's basically saying how many revolutions per minute. So how do we convert seconds into minutes? We times by that. So RPM equals 2 times 60 equals 120 RPM, revolutions per minute. Hope that makes sense. There's a few things you have to do to that. So just have a look at the example above, have a look at mine again. Hopefully you're okay with that. This one's about the accuracy or the resolution again. Obviously, the accuracy is going to be a 40th, sorry. It's going to be a 40th. If you've got 40 slots, then obviously the smallest thing is going to be a 40th. So I'm just going to write that one down. So resolution equals a 40th. So therefore, it's basically what is the accuracy of this? Well, therefore, it's going to be accurate. It's going to be 120 revolutions plus or minus, a 40th of, can't do a 40th, why do I keep doing a fourth? A 40th of that. If you put that into your calculator, you will find it's plus or minus 3. I keep forgetting to put zeros on. What's going on? Yeah? Okay, so therefore the speed can go between 117 and 123 revs per minute. Yeah, that's what it's trying to say. That'll be the accuracy of that. So you have to find a resolution first. It's obviously plus or minus that number. Okay. Again, I hope that makes sense. Read that bit above. This bit's hopefully straightforward. And then going back to this bit, it's just using the equation. It is on the data sheet. However, on the data sheet, it's this. I'll just write it again. So the data sheet says resolution. It's actually the voltage over 2 to the n, because generally speaking, resolution, we do this with, do you remember analog to digital converters? It's the smallest voltage step. Doesn't have to be voltage there. We're talking about the angle for this one. So these bits can be interchanged. I hope that makes sense why you can still do it with an angle, because it's just the smallest increment you can measure. So on a voltage scale, it's voltage. In an angular scale, it's the angle. Okay. Thank you very much. I'll speak to you soon.